The sun. With a surface temperature of 6,000 degrees Celsius, it bathes the solar system with light. Here on Earth, I can use a magnifying glass to concentrate a tiny patch of sunlight to a point hot enough to light a fire. This is the energy that is locked in coal and oil, that changes night into day, that makes the rain, that drives the wind in the ocean currents, and makes all life possible. Since before the beginning of recorded history, humanity has been fascinated and awed by the sun. Until 1960, it was almost inconceivable that a device created by scientists could equal or exceed the brilliance of sunlight. Yet, such a device was invented. In 1960, scientists discovered the laser, light amplification by the stimulated emission of radiation, a new form of concentrated light, more powerful than sunlight. In 30 years, the laser has grown from a scientific curiosity into an indispensable tool of doctors, scientists, and engineers that has affected the lives of every one of us. Lasers can entertain. Lasers can heal. With these bloodless scalpels, eye surgery that would once have been impossible is now routine. Before the laser, this man would have gone blind. Lasers can also destroy with surgical precision, guiding bombs with deadly accuracy. Used in the storage and display of information, lasers are changing the way we learn. And with the help of lasers, we can navigate the skies with pinpoint accuracy. In this laser gyro built by Lytton of Toronto, two intersecting light beams detect the slightest change of direction, generating the numbers the autopilot needs to keep an airliner on course. Lasers can also navigate underground. The machines that dug the Channel Tunnel maintained their course by following laser beams through the rock. Lasers are transforming industry. This will become an artificial hip joint, rendered by computer-aided design and ready for transformation into reality by stereolithography. The computer slices the design into thin layers. The contours are traced by laser in a liquid plastic that hardens when exposed to ultraviolet light. A process that would take a human model maker days is completed in a matter of hours. Layer by layer, the laser recreates a precise replica of the computer-aided design, a prototype ready for testing, modification, or speedy translation into a manufacturer's mold. A laser beam is the ideal cutting tool. Sharper than any blade, it leaves no waste and never touches the workpiece, so it can't wear out. Laser-equipped robots are light, agile, and very accurate. Lasers can cut just about anything with superb precision. These wooden trophy plaques were the first products made by the Laser Machining Center in Toronto. The heat of a laser cuts a material by vaporizing it. Because of this intensity, lasers can machine materials that are too hard or too brittle to be worked in any other way. This intensity is just one of the properties of laser light that makes it so useful. Where does its story begin? 3 centuries ago, Sir Isaac Newton split sunlight into the rainbow colors of the spectrum and brought the study of light into the realm of modern science. Later scientists realized that light exists as particles and as waves, and that each color corresponds to a specific wavelength. Laser light is very different from the light produced by a flashlight. The seemingly white light is actually composed of all of the colors of the spectrum. with different wavelengths pouring out in all directions. Even with a reflector, to focus the light into a beam, it quickly disperses and fades into darkness. When matter is energized by heat or electricity, the electrons surrounding its atoms jump to a more excited energy state. They drop back to the less excited state by releasing this energy as photons of light. This is the spontaneous emission of radiation, and this is the nature of ordinary visible light. In 1917, Albert Einstein predicted the stimulated emission of radiation. He told a friend, "A brilliant light has dawned upon me." The atoms of some materials remain in the excited state longer than others. When these atoms are stimulated to release light by the atoms around them, two identical photons are emitted for every one that enters. If these photons are confined by mirrors, a chain reaction quickly builds up, leading to a population inversion in which stimulated atoms outnumber unstimulated atoms. A laser is built a bit like a fluorescent tube. It's filled with a lasing medium, in this case a gas, which is energized by a pair of electrodes. At either end are mirrors, one of them partially silvered to let the laser beam through. When energy is supplied to the lasing medium, light rebounds between the mirrors, stimulating the atoms to release pairs of photons. These are identical in both direction and wavelength. The light energy builds up rapidly between the mirrors until it pours out of the partially silvered end in a stream of laser light. Laser light is monochromatic, a single wavelength with just one pure color. Laser light is also coherent. Its waves move in perfect unison instead of jostling in all directions and dispersing like ordinary light. And laser light is much more intense than ordinary light. White light is incoherent, with photons of many wavelengths dispersing in all directions. Coherent laser light has photons of identical wavelength, all proceeding in the same direction without dispersion. A laser beam disperses so little, it can be bounced off the moon and reflected back to Earth, measuring the distance between Earth and moon to within a few millimeters. By the late 1950s, scientists knew the laser could become a reality. Theodore Maiman was one of many in the race to invent it.
Friends of mine have described it as a technical Olympics because you had senior scientists from all over the world competing to try to make coherent light. And it was obvious that if you could do this, this would be a technological breakthrough. But coherent light had never been made before. A laser had never been made. There were questions on whether you could do it at all.
Theodore Maiman built the world's first laser at Hughes Laboratories in California in May 1960.
This is the very first laser right here, and the heart of this first laser is this synthetic ruby crystal. The end of the crystal, as you can see, is very flat, and it's been coated to reflect light which goes back and forth within the crystal. This lamp right here is a very powerful photographic quartz strobe lamp which is used to excite the ruby crystal, put the energy into it. And this cylinder here, just the polished aluminum cylinder, is just to contain and get more of the light into the ruby. And so that is the whole laser, and the beam emanates from this end. And the brightness of that light is about 10,000 times stronger than the surface of the sun.
In the first years after the laser's invention, few people could see any real use for it. It was a curiosity, a solution in search of a problem, or even modern science's reinvention of the pin. first public excitement created by the laser was in science fiction. Writers seized on it as the ultimate weapon they had dreamed of for decades.
There were major headlines in most of the, certainly the U.S. papers, which talked about some variation on a theme of L.A. man discovers science fiction death ray.
In 1983, President Reagan, convinced that fiction could become reality, launched the Strategic Defense Initiative, Star Wars. Lasers would be crucial in a space-based missile defense that would make the world immune from nuclear attack. One of many scientists who scorned the project from the beginning was laser pioneer and Nobel laureate John Polanyi of the University of Toronto.
Every branch of physics was recruited. I mean, ultraviolet beams and X-ray beams and proton beams and neutron beams, etc. And the reason that this proposal was flawed, technically the reason is sort of evident around you in this laboratory, and that is that the high tech that you would need, the very highest tech that you would need in order to guarantee that you were going to destroy these missiles, and it takes very few to getting through to do damage. The high tech that you need is easier to undermine than it is to emplace and make work. And what I'm trying to say is that I could run around this laboratory and make each of these machines malfunction. Give me 10 seconds and I can do it. To make them work, I'm not sure I could do it if you gave me 10 months. My students are much better at it than I am.
But lasers do have a role in space, as the eyes of robots. Nestor Burtnick of the National Research Council.
We are trying to deal with the man-robot combination, telerobots we call this, and the current method to do that is to use teleoperation, where the operator basically controls the robot by direct control with a joystick or some hand controller. Now this is a very tedious job for the operator, and what we're trying to do is to find a way of having the robot do some of these tasks autonomously under the supervision of the operator. We're focusing on the problems associated with robotics for the space station. Canada is building the mobile servicing system, and one part of that is a two-armed robot. The role of the laser is to provide a measurement system where it can gather the three-dimensional coordinates of each point where the laser points, and from this you can get a real shape representation of objects from which it can determine their exact position.
Using information from the laser scanner, the robot recognizes the grapple fixture and computes its precise distance and orientation. The grappler can then seize the component and move it precisely without risk of damage. The special purpose dexterous manipulator, under development at Spar Aerospace of Toronto. This test simulates the problem of moving a section of the space station. The laser's capacity for precise measurement provides the exact distance from the manipulator's grappler to every point on the grapple fixture. Knowing these distances, the computer can determine the component's precise orientation. It then relies on its artificial intelligence to finish the job. Human involvement is limited to giving the machine its orders. The robot's three-dimensional laser vision is much more precise than the two-dimensional video image that would be used if a human were to control it. This accuracy is critical for working in space because though spectacular, spacewalks are extremely dangerous. But giving sight to machines is only part of the story. Even before it was invented, scientists knew coherent light could create a communications revolution. Around the time the laser was invented, glass makers were also perfecting fiber optics. Strands of glass with the thickness of a human hair and capable of transmitting coherent light over long distances with little loss of intensity. Laser light moving through glass is ideal for carrying information. Copper wires that the new technology replaces could each carry a couple of dozen conversations simultaneously. A pair of optical fibers can carry tens of thousands of conversations and quantities of computer and video data that the old technology can hardly begin to handle. This is a laser fiber optics communications driver. The laser, a chip of indium phosphide smaller than a grain of salt, can be switched on and off 4 billion times a second. It's this fantastic switching speed that allows a laser to transmit so much information down an optical fiber. In laser fiber optic communications, digitized information is carried on pulses of laser light. Two phones are linked by two optical fibers, but by assigning each pair of phones a place in a sequence of pulses, these fibers can carry thousands of conversations, a process called time division multiplexing. With the laser flashing 4 billion times a second and decoders at either end of the fiber link to direct the traffic, a pair of fibers can handle more than 32,000 simultaneous conversations. Development of laser fiber optic telecommunications is vital to a country as huge as Canada, as vital as the railway of the past and the airlines of today. With the population concentrated in a few big cities or scattered across the second largest country on Earth, it's essential for us to communicate with each other, even though we may never see each other face to face. Canada's geography has encouraged it to become a world leader in communications technology. At Northern Telecom near Ottawa, they manufacture the laser drivers that send optical signals through fiber optic cables all over the world. More important than the number of conversations that may be packed into these fibers is the density of high-quality digital information they can carry. Not only voice, but music, still and moving pictures, text and computer data. Soon, it should be possible for many people to live and work wherever they want and to be in contact with the whole world. At the Ontario Light and Laser Research Centre in Toronto, new, faster semiconductor lasers are being developed by a team led by Henry Van Driel.
All these technologies use solid-state components, and these components are becoming smaller and smaller and are being required to handle information at a higher and higher rate. And what we'd like to be able to do with these very short pulse lasers is determine the speeds at which these electronic devices can ultimately operate.
Higher switching speeds mean greater communication capacity. Existing communications lasers emit pulses lasting less than 1/1000th of a second. Working with new semiconductors, these researchers are producing pulses 1,000 times shorter, measured in picoseconds.
Roughly speaking, it takes approximately 1 second for light to go from the Earth to the Moon. In 1 picosecond, light travels the distance which is equivalent to the thickness of your fingernail.
Lasers can be used in the storage and retrieval as well as the movement of information. Digitized sound is etched onto a compact disc in a spiral of microscopic pits and ridges. Laser light is reflected by the ridges onto a diode, which converts it into electrical energy. These pulses are then transformed back into sound by the CD player's electronics. A CD can record anything in digital form: sounds, music, printed text, or picture. This is a video disc. With the capacity to store so much information, it promises to transform the nature of books and the way we learn from them. Here's my favorite molecule, DNA. A video disc can store 54,000 pages of text, 54,000 still pictures, or half an hour of randomly accessible video with 2 soundtracks. Accessing the information on a video disc is easy. The latest disc players come equipped with a barcode reader, similar to the ones used in a supermarket. Each item on an index of video discs has a barcode, with the codes corresponding to the titles or the first frame of a video sequence stored on the video disc. The barcode reader is a laser. It scans the code and transmits it to the player. The player finds the right frame instantly and throws it up on the monitor. This educational unit on weather first shows a tornado in action. Here, under a different heading, a sequence of computer animation which illustrates the complex process of wound healing. Red blood cells pour out of a severed capillary. White cells move in to devour the bacteria that could cause infection. Video discs are changing the way we learn. At River Oak School in Oakville, Ontario, the students study not with books, but with computers and video discs. Watching a segment on animal behavior, Andrew and Kurt hear sounds and see moving pictures.
Yeah, you don't have to turn the page or anything. You can just go to chapter search and type in 56 and it'll take you to something like Nile crocodile or something like that. So you don't have to look in table of contents or anything. They show you what really happens.
You can actually hear the sounds that they make in the forest, like their normal habitat.
Sounds.
It's not just like made up.
Yeah.
At the National Research Council, Alex Sabo is working on a process that could increase the capacity of CDs and video discs thousands or millions of times over.
It uses crystals, this tiny little crystal, in which the laser burns a hole, if you like, or bleaches a narrow part of the color out. Then if we change the color of the laser, the crystal looks blank again and we can rewrite information into it.
The process is called spectral hole burning. When a laser scans the crystal, its molecules react so that the specific color of the laser is bleached out in a sequence of pits. When a laser of the same color scans the crystal, it detects the pits and reads out the information stored in them. Using a different color laser creates a new set of spectral holes. The first set of holes is not affected by the new color of light. After information has been written into the ruby in several different colors, lasers scan the crystal to read it. The light which retrieves a piece of information must be identical in color to the laser that wrote it. Information written by lasers of different colors is ignored. In reality, the crystal is only affected by a narrow band of wavelengths in the red part of the spectrum. To our eyes, these shades of red look identical, but for the crystal, they represent millions of distinct colors. Each of these colors may be used to store a different piece of information in the ruby.
A crystal like this can store up to 10 million different colors. So for example, if we made the storage of this compact disc color sensitive, where now the color of the laser mattered in reading it out and recording it, we could put, in principle, as many as 10 million compact discs onto one disc.
13 years before the laser was invented, it was predicted that coherent light could be used to make three-dimensional images called holograms. In 1965, holography became a reality. Here at the Ontario College of Art, Michael Page makes holograms of some of Canada's most priceless historic artifacts, including this, Champlain's astrolabe of 1603. Holograms will allow people in museums everywhere to see the astrolabe without risk of damage to it.
Just want to tip your hat back a little bit here.
Lost for 200 years until it was found in a farmer's field in the last century, the astrolabe was used by Champlain in his navigation through North America.
Hold it there. Okay.
The laser-lit hologram produces a full-size, three-dimensional image. To make a hologram, a laser beam is split in two, an object beam and a reference beam which is aimed directly at a holographic plate. The light waves from the two beams interfere with each other to produce a wavefront that is recorded on the plate. The most remarkable attribute of holograms is their three-dimensional quality. The wave pattern recorded on the glass contains images from myriad points of view. Moving around the hologram reveals these image planes in turn, making the hologram appear three-dimensional. If I smash a laser-lit hologram, I end up not with a broken image, but with a complete hologram inside every fragment. Holography can test objects without destroying them. At Metro Laser in Irvine, California, David Rosenthal investigates the squealing of a disc brake.
We make a hologram of the disc brake, and then we view the hologram and the brake simultaneously while shaking it, and we see lines over the structure. And these lines are a map of how it's vibrating.
An artificially generated squeal aimed at the brake sets it in motion. Holography reveals the pattern of minute vibrations that causes the natural squeal. This information can be used in redesign of the brake that will make it vibration-free. Holographic non-destructive testing can detect otherwise invisible defects in jet engine turbine blades and aircraft tires. It's also being used in the design of the freeway piers that will replace those that collapsed during the 1989 California earthquake. At the National Research Council in Ottawa, lasers create three-dimensional computer images in a process called datography. A red, blue-green laser scans the object to record its color and shape. The laser's accurate measuring ability draws a precise outline of the object's contours, while its three colors combine to record the color of the pot. Easily stored in the computer, images like this may be transmitted anywhere in a matter of seconds. An archaeologist could compare this pot with others like it in museums all over the world. At the Institute of Space and Terrestrial Science in Toronto, Alan Carswell studies change in the atmosphere with LIDAR, light detection and ranging. One concern is ozone.
Ozone is an extremely important component of the atmosphere. First of all, low down in what we call the troposphere, the ozone is increasing. And since ozone is essentially a toxic or a noxious gas, this is a concern. Whereas the more widely reported problem in the high atmosphere, in the stratosphere, where we need the ozone to protect us from the ultraviolet, the ozone is now known to be decreasing.
The laser identifies gases as well as the density, composition, and movement of clouds.
Clouds are one of the least well understood components, largely because they're so variable in both space and time, but also because they have a very important impact on the what we call the radiation balance. That is the amount of the sun's energy that's deposited in the atmosphere and on the ground. Clouds are very good reflectors on the one hand, so when it's cloudy it bounces a lot of heat back and therefore cools the earth, but at the same time they're excellent greenhouse constituents. That is, they trap the infrared between the cloud and the ground, so heating is a strong effect of clouds. And right now it's difficult to say if you put clouds in the atmosphere whether the net result is going to be heating or cooling. What we're looking at here is the whole atmosphere from the surface up to an altitude of about 10 kilometers over a 3-hour time period. Each LiDAR pulse generates a single line, and the intensity of the reflected signal from the atmosphere is given a color.
When laser light is reflected by the atmosphere, changes in its wavelength and intensity can identify the chemistry, density, and height of many pollutants, providing crucial information in the assessment of climatic change and atmospheric pollution. While the laser has had an enormous impact on communications and industry, in medicine, its effect has been nothing short of revolutionary.
After the break, the laser's double-edged sword, new ways of healing and new ways of killing.
This is a surgical laser, sometimes called a bloodless scalpel, because of its capacity to cut finer than any blade and to cauterize an incision and stop it from bleeding. Surgical lasers can weld as well as cut, and by choosing lasers of appropriate wavelength, surgeons can select the tissues they operate on, removing unhealthy tissue and leaving healthy parts completely unharmed. A birthmark is removed by laser. The blue-green light passes harmlessly through the transparent surface cells, but when it reaches the blood vessels underneath, it coagulates them and restores the skin to a normal color. At Mount Sinai Hospital in Toronto, a laser is used to remove a growth from a patient's vocal cords. Dr. Peter Alberti uses a carbon dioxide laser which produces an invisible but intense infrared beam that cuts through all tissues by vaporizing them. Operating at a distance allows the surgeon easy access to confined spaces such as the throat. A harmless red laser is used as a guide to allow Dr. Alberti to aim the CO2 laser before it is activated. With a conventional scalpel, bleeding is a problem, obscuring the surgeon's view and threatening the patient's airway. But using the laser dramatically reduces the loss of blood.
Final suction. Is that okay?
Dr. Peter Alberti.
The CO2 laser seals blood vessels less than 0.5 millimeter in diameter, which is the size of the biggest blood vessel in the larynx. So all the time we can see. Secondly, with the micromanipulator, it's possible to be very precise where one puts that laser spot. So the amount of normal tissue that is injured is less than there would have been with scissors and knife.
In another room at Mount Sinai, Dr. Mark Mandelkorn operates on a patient who is going blind because the blood vessels of the retina have ruptured, detaching it and spilling blood into the eyeball. The laser passes through the transparent parts of the eye to seal the blood vessels and spot weld the retina back in place, all in a matter of minutes.
We can pass the laser beam through the cornea until it reaches the retina without actually touching the patient. And the effect is the same nearly as if we were going into the eye and cauterizing blood vessels or sealing torn retinas without any surgical cutting.
People with diabetes are particularly prone to problems with blood vessels in the light-sensitive retina that lines the back of the eyeball.
Diabetes is the most common cause of blindness in North America. And the way that people become blind from diabetes is by blood vessels growing into the eye. These blood vessels are very fragile. As they grow in, they tend to rupture. They spill whatever blood they contain into the eye. The blood builds up and blocks any light from getting into the eye. Consequently, this is one way that these patients become blind. The other way is that as the blood vessels grow in, they drag with them the retina and cause the retina to detach. Now, up until about 1970, there was no method that we had available to deal with these blood vessels. We would watch them grow in, knowing what the ultimate outcome would be, and there was nothing we could do to stop them. Hold steady.
Laser treatment can usually be performed on an outpatient basis. The retina may receive as many as 2,000 shots during a procedure that lasts only a few minutes.
Very good. Okay, close your eyes. Sit back.
The results can be dramatic. This is a diseased eye filled with blood spilling from the retina. This is the retina scarred by laser cautery immediately after treatment. 3 months later, the retina has completely healed. Here, laser light is killing brain tumor cells that can't be reached by conventional surgery.
This is the recurrent tumor that has been identified only in the course of the last couple of weeks.
Surgeon Paul Mueller of St. Michael's Hospital, Toronto, removes the visible part of the tumor, but the cancer cells have penetrated deep into the brain where they are intermingled with healthy tissue. Instead of the scalpel, Dr. Mueller uses a new laser technique called photodynamic therapy. Before the operation, the patient ingests a dye that is sensitive to light of a specific color. The dye is absorbed and retained by the tumor cells, but not by the healthy cells. Light diffuses into the brain through a rubber tip inflated with fluid. When the laser is turned on, light floods the brain to react with the dye and kill the cancer cells that have absorbed it. In stark contrast to the laser's role in healing, it has also become an indispensable component of modern warfare. Flying at night, the combat pilot sees with infrared vision. He's also able to fly the plane and deploy its weapons without taking his eyes off the target. This is made possible by a holographic image of the pilot's essential instruments, projected in front of him as a head-up display. The 1991 Gulf War proved the effectiveness of guided weapons, like the Laser Maverick. An observer on the ground pinpoints an enemy tank with a laser designator. Sensors in the missile detect the invisible light beam and follow it down to the target. Once the guidance system has been activated, the missile holds its course. Weapons like this helped kill as many as 100,000 Iraqis. Scientists are often blamed when their discoveries are used for destructive purposes. Maker of the first laser, Theodore Maiman.
It's inevitable if you have any technology that people who make war will try to find a way to use it, and the laser is not unique in that. There was a lot of electronics in the Gulf War. In fact, there was a lot more electronics than there were lasers. It's not my cup of tea. It's not where I would like to see the scientists and brain power of the U.S. concentrated in developing military types of technology, while the U.S. Scientists were developing laser-guided bombs and missiles. The Japanese were developing laser-guided compact disc players and video disc players.
I don't think that you can stop those parts of science that could be exploited for ill and continue with those parts of science that can only be exploited for good. I think that's a naive notion. But that there is something to reproach scientists with, I would agree, and that is that as citizens they have obligations which increase in proportion to their education, and to say that they have not been as active as citizens as their education and their special scientific literacy really makes it necessary for them to be, I think that's a fair reproach. I think we have to do more.
This is NOVA, the world's largest laser at the Lawrence Livermore Laboratory in California. Its goal, laser fusion, that elusive holy grail of cheap, clean, abundant energy. Fusion takes place when atoms of light elements combine to form heavier elements with the release of enormous amounts of energy. This process, that gives us starlight and the heat and light of the sun, is being duplicated at the focal point of NOVA's battery of 10 giant lasers in this spherical target chamber. NOVA's project manager is Eric Storm.
We really try to make miniature stars. It lasts for a very short time, like fractions of a billionth of a second. And the goal is, in fact, to reproduce the same conditions that exist inside the sun or in stars. That is to take hydrogen, or in our case, we don't use hydrogen, we use deuterium and tritium, isotopes of hydrogen, and heat it to about 100 million degrees. And if you get it that hot, then the fusion, the isotopes, deuterium and tritium, fuse and produce helium and a neutron, and releases in the process lots of energy. That's the goal.
Hydrogen atoms consist of a proton and an electron. Deuterium has a neutron added to the nucleus. Tritium has 2 additional neutrons attached to the proton. Tiny glass pellets containing deuterium and tritium drop into the target chamber. NOVA's 10 lasers produce pulses of power that exceed, for 10 billionths of a second, the output of the entire U.S. electrical grid. The atoms fuse to form atoms of helium with the ejection of a neutron and the release of enormous amounts of energy. The goal of these experiments is gain, fusion, with energy out exceeding energy in. Current predictions estimate that 30 years will pass before laser fusion yields commercially viable quantities of energy. If this is achieved, science will have recreated the sun on Earth and achieved control of the most powerful source of energy in the universe, with the help of a device that was once described as a solution in search of a problem. In 3 decades, the laser has become an indispensable tool of science, industry, medicine, and communications, with new uses being found for it almost every day. All this began 75 years ago with the theorizing of Albert Einstein. His ideas began an era of research that has only begun to influence the lives of all of us. In the beginning, inspired by reverence for the sun, scientists sought to understand the nature of light. In doing so, they created lasers brighter than the sun.